We're very thankful for receiving today Dr. Humberto Campins at the Mérida English Library for this very interesting talk. Please give it a big round of applause. Thank you.
It is a real pleasure for me to be back here. Last year I had the privilege of lecturing here with a lot higher temperature and no air conditioning. And it was still a good experience. So I have wanted to come back to the Mérida English Library since then. And Tricia arranged it for me, so I'm delighted to be back. So I'm a professor at the University of Central Florida, and there we have a Center for Lunar and Asteroid Surface Science, which is a center that is funded by NASA. At UCF, we have a Center for Microgravity. And then a couple of years ago, I received a fellowship to work at the US State Department in the Office of American Spaces, which has nothing to do with outer space. But I became a science advisor for the State Department. And in part because of that, I ended up in this, with opportunities like this one to go and speak about what I do in my research in places outside the US. Here's the outline of what I'll be telling you about today. I'll discuss very briefly the chances of an asteroid impact. And then I'll be giving you two current examples of international collaborations to defend our planet from asteroid impacts. And then I'll give you details on both and end with some conclusions. How likely is an asteroid to ruin the day? It's good to know before you leave the house, right? Yeah. And the answer is, as individuals, not very. So none of us here in this room have to worry about an asteroid impact, because the chances of it happening while we are alive are so low that it's just nothing to worry about. However, impacts large enough to have wiped out most of the species on Earth and civilization, it would have wiped out civilization if it existed back then. They have happened and will happen again unless we deflect the asteroid. So as a civilization, we must worry about it. As individuals, no reason to lose sleep over it. And there was a big impact that wiped out about 2/3 of all the species on Earth, including the dinosaurs. And I forgot where it happened. It just Chicxulub. Where is that? Is that near here?
Yes.
No, I've been studying this area, from the geologic point of view on the crater since I was a graduate student. This is an amazing place. As a matter of fact, when I was a graduate student, it was determined that the impact had happened here while I was in graduate school. And so the dinosaurs did not have a program to defend the Earth against dinosaurs. And they ended up with a very bad outcome. Asteroid impacts can be mitigated or eliminated. And how do we protect our planet? Well, first of all, we study the orbits. We study as many asteroids as we can detect. Study the orbits, and we can determine which ones are in potentially hazardous orbits. So we focus on those, and if necessary, we can try to deflect them if one is threatening Earth. Should I speak a little louder, or?
It's just like, I have to do this to clarify your words. It's just my hearing.
Okay.
My hearing aids are broken right now.
I can use the microphone.
Okay, that might help. Thanks.
Okay. And some asteroids, so right now, as I mentioned, none of them are threatening Earth with an impact, but some are potentially hazardous, which means that even though their orbit is not threatening Earth now, they could in the future as the orbit evolves. And two of them are asteroids Bennu and Ryugu, to which there were two spacecraft, one from NASA and one from the Japanese Space Agency, that went to these asteroids studied them, picked up samples, and brought them back to Earth for analysis. And I'll be giving you some more details about those. So I call it a tale of two asteroids, where you have potentially hazardous asteroids, which are not an immediate threat to Earth, but in another 140, 150 years, we may have to deflect Bennu. And they have similar orbits, and NASA sent OSIRIS-REx to Bennu, and JAXA sent Hayabusa to Ryugu. NASA has an Office of Planetary Defense and Coordination. It includes international cooperation that I'll be telling you about. And it was featured on a relatively recent movie called Don't Look Up. Has anybody seen that? Okay. Now, the head of that office was featured in the movie. Not himself, but there was a character who was playing him. And that person, they discover a comet that's going to hit Earth, and then they reacted. I'll give you more details in a moment. Now, it turns out that my colleagues at the Office of Planetary Defense Office at NASA are much cooler than the movie. They're much more with it, and this little thing was supposed to be here, but Bill Gates and Steve Jobs don't get along, so I prepared this on a Mac, and this is a PC, so anyway, but the point is, I actually went to college with the head of the Planetary Defense Office at NASA. And Lindy, the person who's in that position, would not bring a professor of astronomy from Michigan State and his graduate student, even if the graduate student is Jennifer Lawrence. He would not bring them to the White House to talk to the president. He would filter that information, but the point is, we are in better hands than what the movie made it look like. Now, there are two current examples of international collaboration in terms of defending our planet against asteroid impacts. One of them is the collaboration between NASA and Japan, or NASA and JAXA, on OSIRIS-REx and Hayabusa 2. And the other one is the NASA DART mission impacted an asteroid to change its trajectory. It was a huge success, and I'll tell you more about that. And that is being done in collaboration with the Italian Space Agency and with the European Space Agency. So Hayabusa 2 went to asteroid Bennu, asteroid Ryugu, and delivered the samples back to Earth. OSIRIS-REx went to asteroid Bennu, picked up a sample, and delivered that sample back to the Utah Desert initially, and eventually to the Johnson Space Center in Houston. And as I mentioned, these two asteroids have somewhat similar orbits, and here are the orbits. The orbit of Bennu is similar to that of Earth, but it goes a little further away and comes a little closer to the Sun than that of the Earth, which is in green here. It's got a very small inclination with respect to the Earth's orbit, so it's relatively easy for us to get there, which also means that it's relatively easy for that orbit to change and get to us. So that's what makes it a potentially hazardous asteroid. Here's Ryugu, the asteroid to which the Japanese Space Agency sent their mission. And its orbit comes and basically touches that of the Earth and goes back out and touches that of Mars. And in giving this talk, a different audience member asked me a while back, they looked at the orbit and they said, wait a second, could we use that asteroid to transport supplies to Mars? We catch it when it's close to the Earth, right? We put some stuff on it, we wait until it goes to the orbit of Mars and take the stuff off. It is theoretically possible, but the alignment of the asteroid with Earth and the asteroid with Mars doesn't happen very often. It can be several decades until they align. So if you're not in a hurry for your supplies to be delivered to Mars, you've got free transportation, or cheap transportation. But anyway, the point is they both have orbits similar to that of Earth, and that's one of the reasons why they got selected for these two missions. So here's asteroid Bennu, 101955. Don't you wake up every morning saying, I wonder where 101955 Bennu is. And when we got got there in December of 2018, we got these images, and we were delighted with our initial results. Turns out that here's the asteroid Ryugu. When the Japanese Space Agency spacecraft got to it, they're similar. Ryugu is about twice the diameter of Bennu, and I'll tell you a little bit more about OSIRIS-REx and then go back to both of these asteroids. This mission was justified on 4 major themes. One was revealing solar system history, which was to bring back samples from an asteroid that is sufficiently primitive. It has not changed since its form, since its originally formed, that it tells us about what happened back then when the solar system was formed. The other one would be mitigate impact hazard. So going to these 2 potentially hazardous asteroids, learning about them in case we have to deflect them in the future. Also, enabling a human exploration. Humans want to go to Mars. In order to get to Mars, chances are we're going to have to stop at the moons of Mars, which are both captured asteroids. The most likely mission would be to send a spacecraft from Earth to the moons of Mars, and then refuel at the moons of Mars and take a smaller capsule, a smaller craft to the surface of Mars, back up to the moons of Mars, and then bring the large spacecraft back to Earth. And so this is what would probably be like, and it would be important for astronauts to train on the surfaces of asteroids. So we're helping contribute to that. And then lastly, and very importantly, is developing a space economy. It turns out that above the Earth's atmosphere, there are materials that are very expensive and precious that you can find in asteroids. Anybody want to guess one of those materials?
Gold, platinum. Water.
Yeah, gold, platinum are important, but water is most useful, most precious, because you can split water into hydrogen and oxygen and you have excellent fuel. And there's a whole bunch of Earth orbiting satellites that need fuel. If you can mine it cheaper than you can put it into orbit, then you have a whole set of customers that are going to buy the water that you produce from here. And then that will stimulate more mining where you can extract gold, platinum, and rare earths for electronic circuits, etc. And so there will be a self-sustaining space economy where the water from here goes to the Earth orbiting satellites, plus who knows what else, including, for example, the fact that you could use raw material from the asteroid, feed it into a 3D printing spacecraft that will print the structure of solar collectors or other structures that will operate at the 0G environment of Earth's orbit and not at the 1G environment of Earth's surface. So you may be able to print structures that will be impossible to build on Earth and then put into orbit. And they don't even have to withstand the gravity of the surface because they can operate out there. So this is likely going to revolutionize the building of spacecraft structure. In addition, imagine something like, or not in addition, but as an example, imagine the James Webb Space Telescope, which is a very sophisticated instrument. And in order for James Webb to be launched, they had to build it in a way that it could fold onto itself, and then put it into this tube, and shake it, and launch it, and then open it up in space. What if we had been able to print most of its structure up there, and then send only the components that cannot be printed in space? So it would make it cheaper and also allow you to build things that we haven't even thought about because of not having that capability. Anyway, so the space economy is going to be a very interesting thing to watch in the next decade or two. To remind you, most asteroids are between Mars and Jupiter. Some of them get close to the Earth. We call them near-Earth asteroids and are in red here. And So Bennu and Ryugu are both near-Earth asteroids, and they are, as I mentioned, potentially hazardous asteroids.
Every single dot represents an asteroid
Yeah.
in the picture?
Every single dot. The dots are actually smaller than they look here in space,
Yeah.
right? But yes, the near space is pretty crowded,
Yeah.
and so we need to be monitoring them and
Constantly.
preparing just in case. Yeah. The other thing that I wanted to point out is like, okay, he said that the red ones are near asteroids.
Mhm.
These guys are near Jupiter. What's he talking about? This guy has an elliptical orbit, and it can come really close to the Earth and go back out. Right? So all of those that are in red here eventually get close to the Earth. And we've got a whole catalog, and none of the big ones are threatening us right now. We need to continuously monitor. And then we've got go ahead.
Are we allowed to ask questions?
Of course, and please do. It's going to make
Well, what you said earlier, first of all, the size, I'm trying to get an idea of size. I mean, if we've got a universe filled with big lumps of rock, I mean, you're saying nothing to worry about. Are we talking about little lumps, or are we talking about things the size of this room?
Good question. The majority of what you see here are 1 kilometer or bigger, which are capable of devastating civilization because of the consequences of the impact. Right? The smaller ones are even more numerous and harder to see. But it gets to a point about the size of a bus where they don't survive the atmospheric entry. So anything bigger than about a bus is a threat, but that would be a threat to a small area. And if the area is not populated, or if it's the ocean, then we don't have as much to worry about. If it's populated and it gets discovered at the last minute, we could evacuate. But the idea is to try to deflect them if we didn't have enough lead time. Okay, these are. Yeah, and by the way, I encourage questions. It makes the presentation a lot more interesting.
I did have a question about you had the red and the green, and you had some blue in
Yes.
the previous. Are those?
Yeah, the blue are the Trojan asteroids, which are in the same orbit as Jupiter, but behind or ahead of it. These are areas of stable orbits, where if an asteroid or anything ended up drifting, they end up staying there. And so the Trojan clouds are almost as numerous as the main asteroid belt, but they look different to us, and there's a mission on the way to those asteroids called Lucy. So NASA is sending a spacecraft that's going to observe several on both clouds and to try to understand them better. They're far away, they're dark, so they're less known than these guys, which are closer, and they range from dark to not so dark, but these are all dark and all far away. So studying them is challenging. So these are all the asteroids that have been visited by spacecraft. The great majority of them have been visited in what we call a flyby, where the spacecraft is on its way somewhere else, and it happens to fly near the asteroid, takes a few images with some spectra, and goes on into its orbit. Some of them have been random missions, including the near Shoemaker one with asteroid Hera, and then the Hayabusa mission to asteroid Itokawa, the Hayabusa 2 mission to asteroid Ryugu, and the OSIRIS-REx to asteroid Bennu. Before we got this,
I'm just wondering, like, what kind of technologies used to kind of like push away the asteroids to get close to Earth? Like,
I'll discuss a little bit of that later.
Perfect.
But we are developing at least 3 types of technology. One of them is called the ion engine push. The number one is kinetic impact. The ion engine push, and the last one is being considered, although it's not favorite, which is to send an atomic bomb. Right? But the problem with the atomic bomb is that we don't know exactly how the asteroid will respond to it. What if we just disperse it?
yeah.
And we get a shower of smaller ones, which would be even worse. Right? So we have to be careful. Good question. Well, they're all good questions. You're a great audience, better than my students in Orlando. And so before we got to these two asteroids, we had predicted what we would find. And so in the case, so we had predicted the global properties, the spin top shape, the radiation rate, the rough composition of a surface of very hydrated minerals like clay, and that's what we found. So in the case of Bennu, we had observed it with a radar using the Arecibo radio telescope in Puerto Rico, and we got a very, very good shape and rotation rate. That's what we found. And in the case of Ryugu, it had not come as close to the Earth, so our preliminary shape was close, not as good as Bennu, but still pretty darn good. So, hey, we anticipated this stuff. We're such good scientists.
You know, the small one below 500 meters of diameter, a Mérida city block is 200 meters. So 2.5 blocks wide. It's a small little lump of clay.
It's not a small little lump of clay when it's coming at Earth at approximately, it's coming, and it's also coming at Earth at approximately 60 kilometers per second.
Wow.
So so when this thing comes through the atmosphere, it barely feels it, right? It just boom hits the surface, and it's not slowed much by the atmosphere.
Are you going to get to a point where we talk about how many of these things are hitting the Earth every day?
Not many, but I'll get to that.
Okay.
So let me go back to the fact that we were so good, you just right? Because we predicted all this, and this is what we found. Ha! And we had planned the spacecraft to come down to a surface of the asteroid where we were expecting smooth sand or pebbles, right? And since we were so successful at predicting all those things, we expected that our predictions of the smooth sand or pebbles to be the case. Coarse sand or pebbles? This, just to give you an idea, this is about 3 meters tall. So I would not want to put a beach towel on that because it would not be comfortable to read a book there. So we had very good reason. Yeah, go ahead.
What's the gravity?
It's about 100,000 times less than that on Earth. So
Is
this
there a magnetic field as well?
No. Well, yeah, there is no magnetic field. We did have magnetometers, but there's no magnetic field there. There's magnetic fields are usually generated by a liquid core of a planet or a moon that is rotating and doing the dynamo effect that generates a magnetic field. There wasn't any here. But this was a problem for us because we had reasons to believe that the surface of this asteroid should have nice beachy areas, kind of like Progreso, where you could have a sand and put your beach towel, and the spacecraft would come down and sample that material without the threat of big rocks around you. And not the case, right? And so we were not as smart as we thought we were. And so once the spacecraft is there, we find this out. So we have to reprogram the spacecraft to come down to the surface with a different technique than we had before. Because instead of coming down with an altimeter that all it tells you is how far from the surface you are, we had to upload a system that would allow the spacecraft to correct its trajectory and make sure that if it was headed towards this rock, it would change, and if it was headed towards that rock, it would change and sample the area that we wanted. Right? So they uploaded the software, they tested it, we had 2 rehearsals, and so this is the artist's conception of what we were going to find. Notice that we put this in the proposal to NASA, and we won, and they gave us the $650 million to build the spacecraft and operate it. But notice that our artist's conception back in 2010, when we did this, didn't have any rocks, right? And the artist didn't put any rocks because the scientists didn't tell them to put any rocks in there. And so remember, this is Bennu. It's rotating, it's very rocky, and so when we approach the asteroid, we have to match speed with the surface as it's rotating, and also come down with a very small vertical speed. So zero horizontal speed and very small vertical speed to do the sampling. Which is, my hat is off to the navigation team. I was on the imaging team. And navigation team did a great job. So the point is, they had to figure all this out with the spacecraft already there. There was no chance of testing it here. So this is what we put in the proposal. This is an artist's conception of what actually happened. This is what it probably looked like from the surface as Osiris-Rex was coming down with its mechanical arm deployed and ready to sample. Had we put this on our proposal, NASA would have probably told us, bye-bye, you don't get any money, right? But they did. They gave us money, and we succeeded. But that's what happens with exploration. When you're going someplace for the first time, you have to be prepared for unexpected things. So this is, again, an artist's conception of how we did the sampling. So the mechanical arm is deployed, it is coming down, and it's going to touch the surface. And then I'm going to show you some more artist's conception of what happened based on the images that the spacecraft took. So we touch the surface, we fire this nitrogen that fluidizes the dust and puts it into the canister for sampling, right? And so this is probably what was happening. And this is another view of what we were doing. And notice these big rocks all around our sampling site. So by the way, the team nicknamed one of those rocks Mount Doom from Lord of the Rings. And we have to be very careful not to go one way or the other, because originally the plan was, when we thought this was going to be what we were going to find, that we were going to need an area of about 50 meters across without any rocks. So I was on the imaging team. The navigation team asked us, give us a 50-meter area without any rocks, and we can put the spacecraft safely down, pick up the sample, and back up. Okay, so we get there, and what we see is that, right? So we tell the navigation team, no 50-meter beach. Okay, and they say, well, the spacecraft is navigating so well, we can put it down in half that size, 25 meters. Bang! No, 25 meters. And then they said, what can you offer us? About 8 meters, but with big rocks all around. And that's when they decided to change their approach. Instead of doing it with an altimeter, they had this system where the spacecraft would come, take images, and use those as maps, and then compare the maps with the actual images that it was getting as it was descending and making the corrections. They did 2 rehearsals and eventually the sample maneuver. And so this is the area where we did the contact location. This asteroid was about 160 million kilometers from Earth, and we hit it, and it's rotating every 4.3 hours, and it's all rocky, and we hit the spot that we meant to hit within 72 centimeters.
Wow.
Right? That's good aim. Well, and really good engineers. Okay, so here are the images of the...
Excuse me, how long did it take for this craft to reach the asteroid?
It took us about 2 years to get there,
Yes.
and it took us about 2.5 years to get back.
To the space center, right?
To Earth.
Sure.
Yeah. And from launch to arrival of the asteroid was 2 years, for return was 2.5 years. The Japanese had an advantage because they picked a different asteroid where the orientation was such that they got there in 2 years, but it only took them a year to get back, because as they were doing operations on the asteroid, it was getting closer to Earth. And anyway, but we both succeeded, and actually they got to their asteroid about 6 months before we got to ours. So they shared some of their findings early with us, with the promise that we were not going to steal their results. And that benefited us a lot. We were able to plan for eventualities thanks to the Japanese sharing their data. Yes?
Will you talk about the comparison of the two samples?
A little
Because
bit.
are they similar or are they very, very
They're very similar.
Okay.
Yeah, which is something that puzzles us, because the two asteroids look different when you do remote sensing, but the samples are very similar. Not exactly, but very. So this is our sampling arm. It moves at the last minute to make sure that it's completely parallel to the surface. It touches the surface, it fires its nitrogen gas, fluidizes the dust, and here's another perspective where this is a navigation camera where you can see the actual shadow of our mechanical arm coming towards the surface. It turns out that we had planned, well, that mechanical arm has a coil in there so that when it touches, for example, a rock, it compresses and pushes the spacecraft away. And then we had other backup plans in case that didn't work. It's a good thing we had backup plans because the asteroid never pushed back on the spacecraft. The spring didn't compress. And so the thrusters were fired and the spacecraft moved away. When we analyzed all the data, our conclusion was that had those thrusters not fired, the spacecraft would have buried itself in the asteroid. So your question earlier about what was the gravity, about 100,000 times less than Earth, when you have granular material like this, in very low gravity, it behaves like a fluid. So it was not going to resist the arrival of a slow-moving object, and which is fascinating to us. That's one of the things you learn a lot when you go to a new place. And so we took that sample, we put it into this capsule, and the spacecraft headed back to Earth. It took about 2 years to come back. And then, in the meantime, the Japanese Space Agency did their sample of their asteroid, and they got there. We spent 2 years studying the asteroid before we sampled. We wanted to be sure we understood everything down to the minuscule details for the spacecraft to be safe. The Japanese are so daring. They got there, let's go sample. And they do their first sample. And then they're not satisfied. Okay, that was a sample that was just sitting out there. Let's get a sample from inside the asteroid. So they shoot a missile and hits the asteroid. It opened, not a bomb, but just a kinetic impact. And it creates a crater. So they go and sample the crater so they can sample material that was under the surface. So they brought back 2 samples. And anyway, so they agreed to give us 10% of their sample, and we agreed to give them 10% of our sample. They gave us their sample even before we got back to Earth. They trusted us, which is good. But anyway, now we've given them the 10% of our sample, and we get to analyze 2 asteroids for the price of 1 because of international collaboration. Anyway, so now both of those, the sets of samples are being studied in the labs. Go ahead.
Excuse me, is there any difference between the inner part of the asteroid and the outer? Or, I mean, material-wise,
Yes.
composition-wise?
That's what we're after. One of the things we're after. Right now, it looks like very similar composition, except that the part that was on the surface was exposed to sunlight and solar wind, and it's suffering what we call space weathering.
Okay.
And we wanted to compare what space weathering does to the surface compared to the original composition of the inside, so that when we look at other asteroids, we can correct for space weathering and know what's inside. Does that make sense?
Yeah.
So it's basically you have an old wall that was exposed to the Mérida sun,
Yeah.
and it's fading, and you have a fresh can of paint, and the inside is kind of like a fresh can of paint, and the outside is what's been exposed. So let me tell you a little bit about NASA's DART. It leads the GRQ and the European Space Agency Hera mission. So DART stands for Double Asteroid Redirect Test. This is double asteroid that is not a threat to Earth. Bennu and Ryugu could become threats to Earth. This one doesn't. But it's the ideal system on which to test this, which is to bring a fast-moving object, this NASA spacecraft, hit the smaller one and try to change its orbit and measure it. Right? So it is a test of a technique to deflect an asteroid on a small asteroid that is in orbit around another asteroid the gravity between them is very light, and therefore potentially easy to deflect, so that we can test this method. Again, a tale of two asteroids. Both of them are in orbit around the sun, not a threat to Earth, but the ideal site to test this. And so NASA sends the spacecraft that hits Dimorphos. By the way, this is in perspective, so this is the smaller of the two in orbit around the larger one, because it's far away, but smaller here. And so it hits it, and the idea was to change the period of the smaller asteroid around the bigger one by doing this kinetic impact. Now, the spacecraft was going to get pulverized, actually vaporized during the impact. And so there was an agreement with the Italian Space Agency. They built this Lucia cube, which separated from the NASA spacecraft about 10 days before impact, and took pictures of the impact and went on its orbit somewhere. But the idea was to get a record of the impact itself, and that was successful. Plus, we were sitting here on Earth using Earth-based telescopes to make observations of the impact. This is one of the last pictures that DART took of asteroid Dimorphos. This was the last picture that it took, and then it hit the surface. And this is an image of that asteroid using the Hubble Space Telescope. So you can already tell that a lot of material was ejected, and that material was reflecting sunlight, which is what you see here. So we created a big jet of material that went in the direction opposite of the impact. We were hoping to detect this change in the orbit in a matter of months. We detected it in 2 weeks. The change was much bigger than we had expected. And so now, a month ago, the European Space Agency launched Hera from the Kennedy Space Center, about a 45-minute drive from my house in Orlando. And anyway, so I got to host a lot of my European colleagues for the launch. We had a very successful launch. And the launch came 2 days before Hurricane Milton. So we lucked out. So it's on its way. It will get there in 2026, and it's going to deploy 2 small crafts to make other measurements on the other side of the asteroid on this, and the mothership with all kinds of instruments that are going to look at they call it the crash scene investigation. So it's kind of like crime scene investigation of basically the consequences of the impact of DART onto this small asteroid called Dimorphos. So this is an artist's conception of what that crater should look like. It turns out this is before the impact. It was knowing how much the orbit changed, we think that the whole shape of the asteroid has changed as a result of the impact. It reacted a lot more, mainly because of the low gravity. The consequences were much greater than we had anticipated. And so Hera is going to do this. And so I've been benefiting from the fact that now SpaceX is contracting with the European Space Agency to launch a lot of their spacecraft. And so they're having to come here and they go, hey, Humberto, can you host us there? Can you reserve a meeting room for us to meet while we're there? And I've done that twice, for the Euclid mission last year and for the Hera mission this year. And as a result, I get to work with them more, and I'm going to be collaborating with them on this mission. Right? So, in conclusion, planetary defense against asteroid impacts benefits the entire world, and so it's a good thing that space agencies around the world are collaborating to defend our planet against a possible asteroid impact. One such collaboration is Asteroids and Hayabusa 2 that brought back samples from 2 potentially hazardous asteroids, and then NASA came up with this idea of hitting an asteroid and changing its course. Then Italy contributed the Chia Cube, which imaged some of that impact, and then Hera is now going to go and look at in detail the consequences of the impact. So we are fortunate that international collaboration is giving us an enhanced set of results that individual space agencies might have never achieved. So, thank you. More questions, please? Yes.
Sorry.
Could I hire you to work in my group in Orlando? Yes, ask great questions.
I didn't absorb everything. I was trying to take some photos and remember. When I was that age, you don't remember. But the business about the water, can you go back and talk about because I have a friend, a very political friend, if he was at World War III, he's not going to be about land, he'd be about water. And so what was this thing about the water? Can you go there?
Yeah, the surface of some of these asteroids, especially of Bennu, are hydrated silicates. There is water there. If it was ice, it would have sublimated, it would have evaporated. But because it's bound to the minerals, it's still there. You can extract that water and with certain processes. And the moment you have water out in space, and if you can separate it into hydrogen and oxygen, you can sell it to the Earth's orbiting satellites that might be or will be willing to buy it from you if you sell them cheaper than SpaceX can put them into orbit. What sits on the launch pad is the whole rocket, less than 1% of the mass of what sits on the launch pad makes it to orbit. So it takes a lot of fuel and a lot of infrastructure to get a little bit into orbit. So launching is expensive. Mining asteroids is going to be expensive, but the moment it becomes less expensive than launching, then you have a self-sustaining space economy, where the people that mine the asteroids sell it to the Earth's orbiting satellites, and maybe eventually they could even sell some precious materials to the Earth itself, or to human exploration of the moon itself. So it would be a way to make the whole operation of spacecraft cheaper by mining the asteroids. Plus, once you're there and you're mining for water, you could get other material that you use to print structures.
So I suspect a lot of space exploration has nothing to do with where are people going to live in the future. It's about where are we going to make more money.
Yeah, money is a big motivator. Yes, you're right. But without the investment of governments like Europeans and NASA, this would have never gotten to the point where it's commercially viable, right? You have to make a very big investment that no private corporation could have ever done. So we have to thank the governments of all these space agencies that have contributed. Other questions?
I have a question. I arrived a little late. How many asteroids or on a regular basis are tracked and detoured from hitting Earth? Like, has that happened already, or?
Yeah, hold on. I'm trying to get to the idea. So this is the plot of the asteroids and the main asteroid belt, some of which cross and come near the Earth. We have a few thousand near-Earth asteroids, of which none are threatening Earth with an impact now. But the better our telescopes get, the smaller the asteroids we can track, and the more we can anticipate any impact. When you get to a certain point where they're about the size of a bus, then they're no longer a threat, right? But in between a bus and something that is 500 meters, right? Or what was it, 2.5 blocks? And it's there's a whole range in there. And just as they are potential hazards, they're also potential resources. So there's several private companies, and the government of Luxembourg actually is funding a lot of research on this to mine asteroids. Not just asteroids, but also mine the poles of the moon for water, and use it for human consumption and also for other applications. Other questions?
I have one that's not exactly about the current asteroids, but previous, we were talking about the Chicxulub. I just recently was reading about the one in Antarctica, but it was, I think, an older book from exploration, the one that caused the gravity well, and it said it was many times larger than Chicxulub, and I had never heard.
I heard something about that, but I have not read anything.
Okay.
So, I mean, I saw a headline about something about the structure under the ice in Antarctica that seems to be a big crater.
Yeah, it seems that obviously it was pre-Chicxulub.
Yeah.
Right, most likely.
Well, it depends. I mean, you can determine that from the certificate.
Yeah, but I just didn't know if you knew anything about it, because
No,
I didn't, so.
I don't. Sorry. But it's very possible, just like we have the evidence. The thing with Chicxulub is that we were looking for it because there is this layer in Gubbio, Italy, where you have the Cretaceous and the Tertiary. Dinosaurs, no dinosaurs. And in that KT boundary, there was a lot of iridium, which is not normally found on the surface of the Earth, but it's found in meteorites. So this guy Alvarez proposed that it had come from an impact. And so geologists were looking because the abundance of iridium on wherever you find that layer, which is not necessarily everywhere, but wherever you find that layer, the abundance of iridium tended to increase towards the Caribbean. So they were looking for it in Haiti, they were looking for it, so they were looking for an impact until one of my colleagues, Canadian, was talking to a friend of his who was a commercial pilot that was doing some surveys for Pemex to look at the gravity and try to identify subterranean structures that would be likely to have oil, right? So they're having a beer in Houston, and the guy says, "Yeah, we've been looking for a crater somewhere in the Caribbean." He goes, "You know what? I made this map for Pemex, and it looked kind of like circular." And he goes, so anyway, so make a long story short, eventually the Chicxulub impact was identified. It's under 65 million years of sediments, and it was discovered with this original map that was being made for Pemex.
I hope you have that guy's name and his map to sort of up on the wall at NASA.
Maybe. I don't know. Yeah. Any other questions?
I do. Going back to the question of how often does something approach the Earth or actually impact anywhere on the Earth or get burned in the atmosphere?
Small objects fall every day. We don't know about most of them. Some of them get detected by this system that we have for monitoring nuclear explosion. And so there's a treaty and there's all this monitoring. Also, both the US and our not such close friends would want to know if something that they see bright in the sky is a missile or if it's a meteor or a meteorite. Okay. So a colleague of mine, Canadian, actually has funding from the American government to track this. It's one of the few cases where we actually send funding abroad for science. And his name is Peter Brown, and he follows with this. So they do studies on these bolides so that they can provide the Canadian government and the American government with data that says, don't worry, this is not a Russian missile. And so they have an idea of how often they come and how bright they are. The majority of them fall in the ocean and there's no consequences. Many of them burn up in the atmosphere, never. So what is left is just dust and nothing really solid makes it to the ground. And an impact large enough to cause a civilization collapse happens on average, and that's a very loose word, about 30 million years or so approximately, right? But that doesn't mean that it won't happen tomorrow, or that it won't be another 60 million years until it happens. So that is on average. We want to know better than that, so that's why we're monitoring, and the ones that are not threatening us but could in the future are getting a special attention.
Is it just because of the gravity from the sun that they only go out past Jupiter, or is that the only thing we could measure? Like how many are way past even outside the solar system, or is that even not possible to track? And then,
They're not possible to track. We
Okay.
believe that they are there because often with encounters with Jupiter, they get thrown out of the solar system. And we've seen 2 cases of objects that came into the solar system from another star because their velocity was high enough to not be part of the solar system. And they were interstellar visitors. They were probably ejected from another solar system, a nearby star, and they ended up passing by here, and we were able to identify that they were not bound to the sun. And so it's one of them is called Oumuamua and Comet Morrison, the 2 objects that came from other stars.
did they ever identify the Phoenix asteroid that the Romans talked about?
I'm not familiar with that.
Like Claudius in the 50 AD talked about every 1400 years there was the comet that came around.
I don't know if that's been identified with a periodic comet, but very possibly.
But yeah, but it should be something that they could. I'm just curious if you knew that off the top of your head. Because I read it just recently and I was fascinated that the Romans were tracking back with the Romans and then the Greeks were tracking comets.
Okay,
and
so
I had no idea that.
They found reports of that object, and now they think that
they could have been different ones.
Yeah, well, this is part of the merit of Edmund Halley. He realized that these bright comets that were observed were actually the same one that was coming back, and so he was the first one to say, "Comet Halley, this comet is coming back," and then they gave it the name of Halley. He died before it came back, but he predicted the return of Comet Halley. And by realizing that there was
because that's what he was talking in the it was like his diary. He was talking about, or his autobiography. He was talking about the it's coming, but it's coming back a few hundred years before it's supposed to. The next, and it's like, do you think it could be a different one?
Yeah.
But
no, it's fascinating what historical records can tell us.
Yeah.
And there's also an interesting story about Plinius observing the eruption of Vesuvius and coming down into Pompeii. And he described it. For many years, geologists said Plinius was wrong. It's impossible for a cloud of debris to travel that fast from basically the peak of the volcano down to the valley. The friction with the ground would not allow that. And it turns out Plinius was correct. And it's because all of this debris is outgassing. It's very hot, so there's gases that come in. It creates a cushion of hot gases that allow it to flow down without essentially no friction.
Right.
That's one of the reasons why people in Pompeii were killed, because that cloud came so fast. They had advanced warnings that something was happening, but they didn't know that thing was coming, and it hit them so quickly. But yeah, so they're now called, they've been observed in several places on Earth, and they call Plinian eruptions. When you have the debris creating its own gas cushion that is letting it travel fast. Any questions? You're a great audience. Should I just hold it?
Gracias, Humberto. Thank you so much.
It's not saying it's
Very
me.
interesting.
Thank you. No.
Thank you to the Mérida English Library.
Yes. You want to do it all the time?
Yeah,
Muy
yeah.
interesante. Muy interesante.
Oh, thank you. Is it?
So I'm a live photo.
Yeah, it's fine. Thank you so much. Awesome.
Yeah.
Thank you, Number. I just have a quick question, like regarding my career path for him, because one day he told me like he was interested in math and the subjects. What kind of like studies do you think he will like to be part of this world?
Many. You can do physics, you can do chemistry, you can do engineering, you can do even accounting. Because maybe accountants can be background. So there are many ways in which you can get involved. If he likes the sciences, and you're better at it just because of your passion. Focus on it more. You're going to get ahead. Let him go into whatever he likes. And as I was mentioning earlier, when we talk at the university, and they asked me something similar. I said, there's a quote by an American philosopher, Joseph Campbell, and I'm paraphrasing, but he essentially says, follow your passion, and doors will open when there are only walls. If you do what you like best, opportunities will come that you never anticipated.
Thank you so much. Enjoy the time here. Because you're from Metro Orlando, right?
On Monday.
Oh, Monday, okay. Awesome. Okay, thank you so much. Appreciate it. Enjoy your time here. Hasta luego. Hasta luego. Thanks for the photos. Awesome. Hey. Muy bien. Mira, tengo la familia visitando. Yeah, it's my brother. Mi hermano. Sí, ese es su hijo, mi sobrino. Angelo. Tell her like you went to
Where'd you go? Did you go to Rome?
the moon house. Right? That's what we got to do back, so that's where we go. No, it's Sunday. He doesn't speak in English, just Portuguese. Yeah, that's it.
My daughter does.
Good. So we did that here last Thursday, staying until Sunday. We're gonna go back to Brazil on Sunday. Yeah, just a week. Yeah, because he has a job, he's in school still. So
But he has a week of school.
he's missing a week of school, but I told him like it's a very good opportunity for him. Yeah.
And that's the best experience you can have.
Yeah.
That's why my daughter traveled.
Because that week I'm like, it's easy part, right? But being at the like we went to the museum here, like doing a bunch of cultural stuff. It's so much like it's like exactly good idea. Oh, I don't know how the system works in here, but it's good for him like yeah, we have to he's coming tonight and it'll be out tomorrow. Awesome. Okay, Tricia, thanks so much for putting this together. So nice. Yeah, love that. Awesome. Hasta luego.
We did stuff, but over there, there's one, and but that's just studies. We started I said like 14 to 10 days of working and we worked for years to finish it. We succeeded. And 5 years ago, and we launched it, got there, operated it, brought it back. So if you don't have stupid. If you don't ask the president
I mean, the same thing for you
But they have
Yeah.
a lot of
Yes.
different.
And they have a lot of stuff, right?
I know.
200.
Yes.
So people like that.
And it was exactly because this week is their science.
Oh,
So it
Remember
was
that, but they wanted to come and contract.
perfect. That's exactly right.
They were, and they have an engineering on it.
Yeah, he stopped the endorsement of Harris and Washington.
And the rest were engineers,
I know, some of the
others, but focus, he says this presentation.
No, it's on the call. What's
So
up?
he did, he told them this, and it was really personal. Was
Even it's sad because I don't think we're
engineer
not
to
doing
be in
it.
this.
Because it's not focused, yeah, for.
Because everything they did on the studies and everything, but the actual robot, engineers, so the kids were
Right, so cool.
Yeah.
It's amazing.
What, may I ask what prompted you to leave?
Well, in the beginning, I went to live in England, and I was finishing PhD for UCLA, part of that, because,